Hello and welcome to this Chauvin Arnoux webinar. In this webinar we're going to look at the BS7671 18th edition requirements relating to power quality and energy efficiency. My name's Kevin Smith, I'm Business Development and Marketing Manager here at Chauvin Arnoux in the UK, and I'm going to be your presenter during this webinar. If you'd like to discuss any of the topics raised during the webinar, you can connect with me via LinkedIn. So for those of you who don't know anything about Chauvin Arnoux, we were founded in Paris in 1893 by Raphael Chauvin and René Arnoux. Chauvin Arnoux has played a major role in the history of test and measurement. We have a long and prestigious list of inventions, such as the universal tester, which was the ancestor of the multimeter, and also the current clamp. In the 20th century, more than 350 patents and brands were registered by Chauvin Arnoux. To give you an idea of some of the numbers involved, we have an average annual sales revenue of around 100 million euros. We have 10 subsidiaries spread across the world, of which the UK subsidiary is one. We have 900 employees across 7 production sites and 6 R&D departments worldwide. And we're also very proud to say that we spend around 11% of our revenue on research and development, always ensuring that we get the latest and most up-to-date products within our range. So before we get started, there's a few things I want to talk about to help you get the most out of this session. The first one is testing 1, 2, 3. Please take a moment now just to check that you've got your audio levels adjusted correctly, that you can hear the content, and that you've got a good, reliable and stable internet connection. If you do experience severe problems during the webinar, sometimes logging off and back on again will help you correct those. The session today has a duration of approximately 1 hour, and during that session you can use the questions box to ask any questions as we go. We do have staff on standby to answer your questions during the session, so please feel free to type those questions into the question box during the session. Remember to download the presentation handouts. If you go to the go-to toolbar, you'll see there a section called handouts, and in there's a PDF copy of the presentation slides. So no need to write any notes down or remember all of the content. We've already provided you with a PDF copy of the presentation slides. Now, at some point after the session, usually a few days after the session, you'll be sent a certificate to say that you attended. And also, again, maybe a week after the session, we will release the video of the session to our website, www.cauk.tv, and also on our YouTube channel. So please keep a lookout for those. And you can also visit those sites to see previous webinars that we've uploaded in the past. So with that said, let's get started. So in the webinar, we've called the webinar BS7671 18th edition requirements relating to power quality and energy efficiency. And in this webinar, we're going to cover the general requirements of BS7671, particularly concentrated on parts 1 and part 3. Then we're going to have a look at maximum demand and loading in a bit more detail. We're also going to look in more detail at harmonics, and then we'll finish up with looking at the new appendix 17, which covers energy efficiency. Now, this is something that I hear a lot, particularly I used to train a lot of electricians, and this was something we heard a lot. You know, this stuff doesn't apply to installations I work on, right? Yes, it does. Generally, yes, it does apply to you. A lot of people tend to, when it comes to things like harmonics and stuff like that, they tend to gloss over. They tend to miss it out and just assume, well, that's for posh installations, that's for different installations. It's not for the bits I work on. And actually it is, you know, as you'll see as we go through this session. So I've called this a little bit airing a few truths, and actually there is a few things that, you know, we need to just discuss about these topics. So generally, as you'll see as we go through the regs around these areas aren't particularly well written, because you know, they can be a little bit complicated, and there's not a great amount of understanding of these topics. The regulations aren't written the best, so I'll do my best to take you through them today, but obviously, I say they're not brilliantly well written, and you'll see some little examples in there of where they can be a little bit confusing. Also, as a result, most colleges and training companies don't really talk about these topics. So when you do, when you're at college and you're doing cable calculations and things like that, it's very rare for them to include an example with harmonics in there. Um, Same with maximum demand and things like that. It tends to be done of a very standard approach to it. And I know, that's trying to get the basics over to people first, and you can obviously always move on to these sort of things afterwards. But unless you really do a very, very good design and verification course, even at that, you're unlikely to cover a lot of these topics. So it is something that we want to see more taken up, and we're doing our best to sort of make these topics more accessible and really try and explain to electricians what they need to do. Because in many cases, it's not that difficult. It's just a matter of actually considering it and getting your head around it. And I know, for example, if you're doing an 18th edition course, there really isn't a time on the course to sit down and go through all of this in a lot of detail, and often it just gets missed out. So as a result of that, a lot of electricians know very little about power quality, very little about harmonics and all those sort of things. And that does just mean that if you don't know about it, it tends to be out of sight, out of mind, and people just ignore it, or they don't want to engage with it because it's something that's not included. So can be a little bit difficult, that one. But on the flip side, power quality and energy efficiency is only going to become more important in the future as we start adding more and more non-linear loads, as we start adding things like electric vehicle charging and power walls and all of these sort of electronics into installations. It does become bigger and bigger and bigger part of what we need to do. So now's the time really we need to start looking at power quality and energy efficiency and really get into grips with that as electricians. So in this section, we're going to take a look at the general requirements of BS7671. Chapter 13 of BS7671 outlines the fundamental principles of the regulations and contains many references to power quality topics. So starting off really at the start of the regulations here, section 131, protection for safety. And protection for safety outlines the risks, the things that we need to consider when we're actually designing a safe installation. And there's a couple of points there. Number 4 talks about undervoltages, overvoltages, and electromagnetic disturbances. So again, that's a typical thing. If you remember back to the last webinar, that we talked about things like dips and swells or sags, even transients and spikes and all sorts of things. So again, to be able to determine these things, we might have to carry out a power quality survey to actually get a proper idea of the magnitude, the duration, the types of these things we're going to come up against. And again, in number 6 there, it mentions power supply interruptions. So if we are going to have power supply interruptions, and we know we've got a supply that's subject to power supply interruptions, again, we need to design the installation to cope with that. So sometimes a power quality survey may well be something that we need to carry out right at the start of design and electrical installation. Nature of demand. So nature of demand talks about actually the number and type of circuits that we have, and that we have to think about the demand so that we can actually set up the number and type of circuits in the installation correctly. And again, we mentioned things like the loads expected on various circuits, so we might need to do a load survey. Daily and yearly variations in demand. So again, a load survey would plot the actual variations over a daily period or maybe even a yearly period. And also it mentions there any other special conditions such as harmonics. So when we are determining the number and type of circuits that we lay out, we really do need to know about the loads, any variations in those loads, and also things like harmonics. So again, this is leading us down the route of power quality surveys, or certainly logging, to be able to actually determine these things. Now, I did mention earlier on about actually working out the cross-sectional area of conductors, doing cable calculations. And again, we talk about admissible temperature and volts drop and all those sort of things. But down the list, you'll see number 7 there is actually harmonics. And we will touch on a couple of examples later on in the webinar of how to actually calculate cable cross-sectional areas allowing for harmonics, because that is included in appendix 4. It is in there, so we'll actually touch on that. But again, how many people actually do that? I'm guessing that's very few at the moment, and we need to change that. Now, moving on into part 3, which is assessment of general characteristics. There is a few crossovers, and again, these are probably things we will follow up on later in the webinar. So 311, maximum demand and diversity. So we're familiar with the terms maximum demand, what's the maximum demand the installation is going to place on the supply, and also diversity. How do we allow for variations in that demand? The fact that it's not going to be, fully on all the time. Things will be turning on, turning off, and obviously we're allowed to allow for that within the design of the installation. So again, I'll show you later on some examples, and we'll talk in a bit more detail about maximum demand. Now also 313 supplies actually talks about the characteristics of the available supply or supplies, and it says the following characteristics of the supply or supplies from whatever source and the normal range of those characteristics where appropriate shall be determined by calculation, measurement, inquiry or inspection. And the first one on there, it says the nominal voltage and its characteristics including harmonic distortion. So if we are going to be looking at the supply in there, it does say that we actually need to know not just what the nominal voltage is, but any characteristics of that, so the harmonic distortion. So again, we really need to be able to measure that and actually understand, is there actually any problems with the incoming supply that's going to introduce harmonics and harmonic distortion into our installation that we need to allow for. Now, this one really ticks all the boxes in one go, and if you remember back to the first webinar in this series, we actually talked about the things that we look for when we do a power quality survey, and I think you'll see pretty much everything's on this list. So this is talking about compatibility of characteristics, and it says we should do an assessment of the characteristics of any equipment likely to have harmful effects on electrical equipment or other services or likely to impair the supply. And if you look at what's included in here, transients, undervoltages, unbalanced loads, rapidly fluctuating loads, starting currents, harmonic currents. So all of these things really we talked about, down the bottom there we've got power factor. So these were topics that we talked about that are specifically related to power quality. So again, this section 331 is really driving us to the point where we need to know these things. We need to be able to quantify these things so that we can make the right decisions with regard to equipment and the installation and circuits and protected devices. Now in this section, we're going to take a closer look at maximum demand and diversity. Again, another thing that makes me sob. And I hear this a lot from electricians. I just put down the size of the main fuse, the demand can't be more than that. So this is a very common practice. Electricians, when they get a box on the electrical installation certificate that says maximum demand of the installation, they just say, oh, well, what's the rating of the fuse? 100 amps? Right, we'll put 100 amps down for maximum demand, and they don't give it any more thought than that. Now, we're just going to explore that logic a little bit with a little example. So if we have a look here, this is 100 amp BS7671 fuse, which is the normal sort of fuse you'll find in a mains cutout. And this is the tripping graph for that fuse. So if we were to say we actually overloaded the installation by 2 times, we actually put 200 amps through this 100 amp fuse. So our maximum demand was 200 amps. It was 2 times the rating of the installation. So it's almost like we've got 2 installations joined together. So at the bottom there, we go for 200 amps and we follow that up until it crosses the 100 amp curve. And then we go across to the left there, and you will see that we hit 400 seconds. So actually, just exploring that logic there, if we overload the installation with a BS71 100 amp fuse, at 200 amps, it will take 400 seconds, which I think is about 6 minutes 40, something like that, to go pop. So if we were overloading the installation to say, I don't know, 120 amps, 130 amps, 140 amps, it would very likely almost not go at all if you follow the graph on here. So while it does provide some overload protection, obviously if we severely overloaded it, it would go. The function of the main fuse is to provide fault protection. So if you've got a serious fault, you know, a few thousand amps, it's going to go quickly, and it's going to disconnect your installation. And that's what it's there for. It doesn't limit the maximum demand. Maximum demand is about what's actually being used in the installation. So you'll remember, probably going back when you've done some training in the past, from the on-site guide, we've got table A2, and in table A2 it actually lays out some sort of general rule of thumb type logic we can use if we're actually laying out an installation. And to be honest, if we're designing an installation from scratch, this may be the way we have to do it, because we don't have any data we can actually measure. So if we are doing installation from scratch, we will have to do some sort of method like this. But what this does is it says, right, you know, if we've got some heat and power circuits, we take 100% of the first one plus 75% of the remaining appliances, and we work out our sort of maximum demand in that approach. But again, it's quite old. You know, these things have been in here a long time. They don't really take into account modern usage of electrical installations, modern lighting, for example, the changes in loads. You know, motor drives and all these sort of things aren't really taken into account in this table. So you're always better off, if you can, with actually measuring. If you have got an installation or you've got a very similar installation, but able to actually measure the maximum demand and actually see what it is always a better way of doing it. So what we've got here is actually a load characteristic, a load graph. And this is a load survey that was actually taken over about a week period, about a 1 week period. And this was done using one of our PEL power and energy loggers. And this is just monitoring the current on 3 phases, L1, L2, L3, and a neutral. And you can see the colours on there, the brown, black and grey and the blue to denote that. So this is actually showing you how detailed we can get. You know, we can really get into this and we can start to see what's going on, and off that we could actually start to make some more informed decisions over what the maximum demand for an installation may be. So starting point on here, if we just have a look, you can actually see the days, the grids on here actually are 1 day division, so you can pretty much see the days in here. And you can see the normal days of the week. And I'm guessing here we've probably got, I'm guessing this is probably a Saturday. We've got a few loads on there just in the morning, maybe some single phase loads. So that could be just some office workers or, you know, bits of lighting, something like that on a Saturday. Sunday, absolutely dead. No activity going on there. Although there is a base load. If you look at the base loading there, you know, you're probably talking, you know, on L1, you're looking around probably the 30-40 amps mark, even just as a sort of out of hours figure on a Sunday. So when we talk more about energy efficiency, actually this is a useful activity for that as well. So then we move on, and you can see the actual characteristics of each individual day there, and you can see the sort of start of the day, the way the day looks and the end of it. And obviously, if we're talking about maximum demand on here, just a basic survey like this would actually give us a bit of information, because say this was a 100 amp supply, if this was a 100 amp 3-phase supply, and we look at this, we'd actually be thinking, oh my God, you know, this is overloaded, this installation's overloaded. But it may be a 300 amp supply, you know, it may be bigger than that. So again, once we start looking at this, we're actually making some estimations, but it's based on real data, it's based on the actual figures we can see. And what we can do is we can take that a step further, and we can actually zoom in to a 1 day view. So we can actually take that data and we can continue to zoom in if we wanted to, and really get in on that data. So we can start to see what happens over the course of a day. Now, obviously, we're logging the whole installation here, and you could do this per circuit. You could even do this for particular items of equipment, but this is the whole installation in one go. So we can see that actually activity on this site pretty much seems to start around about 4:30 a.m. Something starts to happen. Maybe people start to come in, maybe a bit of heating kicks in or something like that, and it's starting to build up. The main activity period is from about 6 a.m. through to about 3 p.m. That seems to be when the main activity is going on. So there might be a shift, or there might be opening hours or something that govern that. And you can see we're going, you know, sort of going through that process. But realistically, the loading generally tends to be under about 200 amps all in. It does go over that, but not for huge periods. Again, we'd probably want to zoom in and just have a look at those bits where it's actually gone over, just to see, you know, how much over for how long and things like that, if we're making decisions on what we're going to allow for diversity. Then we get a period between about 3 p.m. and 10 p.m. where the load seems to drop again, but doesn't disappear entirely. And then after 10 p.m. it's pretty quiet in there. Now, in that period between 3 p.m. and 10 p.m, we can see that the loads tend to sort of mirror each other on the phases, but we've still got quite a lot of neutral current, so it does look like it's out of balance quite a bit there. So again, that might just be an indication that there is, you know, improvements or savings to be had by actually improving the balancing within the installation. Because again, when we are looking at maximum demand, and this ties in again what we'll talk about later on with energy efficiency, is sometimes you can identify things where you think, oh, actually, it looks like in this case, maybe the grey phase is not very highly loaded. So could we actually move some circuits onto that? Could we move things around, and that'll actually bring down the overall maximum demand of the installation to a more acceptable level? And if you were going to add equipment onto this, again, you could then have a look and say, well, if I'm going to add a piece of equipment on and it's going to come on at this time of day, it's going to add another 50 amps onto a certain phase, or it's going to be a 3-phase load. Again, you can start to work out when you're doing additions and alterations what the impact of that would be. So you can see it's really powerful having these tools and being able to actually log what's going on over a period of time and then drill down and get the actual data. You know, it's not just sort of 100% of this, 50% of that, and, you know, finger in the air job. It's actually, you've got the proper data to be able to back these things up, and you know that that installation, when you design it, is going to be done right, and you've factored in everything that's going to occur, you know, reasonably within that installation, and you've also got the evidence to back that up as well. So carrying out a logging survey with a PEL, a power and energy logger, or power quality analyzer will give you the best data on which to base your assessment of maximum demand. You will also gather important data about harmonics, power factor, and other useful parameters. You will likely see potential energy savings to investigate too. So in this section, we're going to have a look at what the reg says about harmonics. In total, BS7671 mentions harmonics 81 times. As you've seen earlier, the regulations require us to know what harmonics are present in our installations. You'll remember from part 1 that harmonics are caused by non-linear loads like power supplies and variable frequency drives. But did you know that most clamps can't measure harmonic currents? So this is true. Most clamp meters that you will come across, most normal clamp meters, are often filtered just for the 50 hertz, 60 hertz that they're likely to be measuring. So they don't pick up the frequency bandwidth either side of that. They don't pick up the harmonics. So in a lot of cases, you could be measuring, you know, using your clamp meter, thinking you're measuring the current, but it's not the true current. It's just the current at the fundamental. It's not the current across the whole harmonic spectrum. So if you've got harmonics in there, you're not going to be picking that up unless you use a clamp meter that is specifically designed to do that. Now, in the case of Chauvin Arnoux, we've got two clamps that are harmonic clamps, the F407 and the F607, and they're specifically designed to measure harmonics up to the 25th harmonic. So they will actually give you a true picture of what's going on. So something that's very important if you are actually measuring currents, you're using a clamp meter and you're basing designs on that, just be aware that it may not be. You know, always look at the manufacturer's data and make sure that it has actually got the bandwidth to measure the harmonics as well as just the fundamental frequency. So going back to the statement that was made earlier on, you know, this doesn't apply to me, does it? You know, it doesn't apply to the installations I work on. It's just posh installations. I thought what I'd do is actually do some measurements just to sort of prove what's going on. So in this case, I did some logging, and I measured the percentage current harmonics present in a typical domestic property, in this case, my house. So what you can see is going on here is actually we've got percentage current harmonics. So if you look at number 1 there, the first column, that's the fundamental. That's 50 hertz, and that's obviously 100% because it's based on the size of the fundamental. But what's interesting is when we get to the third harmonic, which remember is 150 hertz, at 150 hertz, we've still got over 50% of the current that we had in the fundamental. And then if we go to the fifth harmonic, again, we're at about 30%. So we've still got 30% of the current, a third basically, of the current that we had in the fundamental in the fifth harmonic. And going on to the seventh harmonic, we're just over 20%. Ninth harmonic, we're at sort of probably about 16, 17%. 11th harmonic, we're still over 10, so, about 12%, something like that, and so on and so on. And what's interesting, you can actually see with the 19th, 21st, and 23rd harmonics, the current actually starts to go back up again, so we've actually got some more harmonics going on, even up at those very, very high frequencies. So you can see here that, if we've got a harmonic clamp meter that actually measures up to the 25th harmonic, we will capture all of that current. Whereas if actually we're just using a clamp meter that's filtered just to measure the fundamental frequency, then we're not actually going to pick that up. Now, we actually recently did a test, and there's a YouTube video, I think, knocking around about this. But we recently did a test using a leading competitor's clamp meter to measure the current of a CFL, a compact fluorescent luminaire. And we actually found that the value measured on the clamp was 2.9 amps. But that was actually less than half what was actually present. What was actually present was 6 amps. So when you take into account the actual current in all of the harmonics, we've got 6 amps there. But using a standard, and this wasn't a cheap clamp meter. This is a good quality, from a good manufacturer's clamp meter. It was measuring less than half what was actually present because it just wasn't designed for the full frequency response. So you do need to be very careful if you're measuring currents that you are actually taking into account the full frequency response. So you can see here, does this actually apply to the type of installations I work on? Well, this is just a simple domestic property. What I had on at the time was things like some lighting, probably LED lights, my PC, power supply, the monitor, laptop, and a few other little bits. Not much on at the time, but you can see the actual harmonic content that created. So the fact that harmonics are present in just a simple, small domestic property is a bit of an eye-opener, but you multiply that by a block of flats, you multiply that by an office block or a factory or, those sort of things. That's where it starts to get more and more and more critical that we take account of these things and we're actually aware of it, because if these are present just in a small installation, they can multiply when the installation gets bigger. So giving you a bit more of an example of a bigger installation here. This is going back to the installation that we did the 1 week logging on. And you can see here, this is the same period. This is sort of the same graph effectively. But in this case, we're showing percentage current THD. And you can see the same sort of alterations over the days. So you can see where the days fitted in there. But there is actually this confusing bit here, which looks like it's got very high harmonics, this period here. And this is where percentage THD can actually be a little bit misleading because it's a percentage. So there's a couple of things going on here. Obviously, at this period, this was where we said this was over the weekend, so there wasn't a lot of current demand going on. But because we're measuring it as a percentage, the actual harmonics seem bigger because they're a greater percentage of that low current demand. So always be careful when you're measuring percentage THD, that if you have got low loads, it can seem, the distortion can seem higher as a percentage. The other thing to be aware of is that a lot of times when you've got things like power supplies, and they're operating at low load, so they're operating at a small percentage of their capacity, they're almost just ticking over. That's where a lot of times a lot of the harmonics are generated, because the power supply is trying to chop that waveform down, you know, because it knows it doesn't need much power. So there's a lot more sort of switching going on in that case. So sometimes when things are lowly, you know, have a low load, they can produce a lot more harmonics. And actually, if you turned on a few more, you know, loads on there and actually loaded things up, the harmonics would decrease quite significantly. So just be aware of that when you are actually monitoring these things, and particularly if you're just measuring it, say with a harmonic clamp, and you're just measuring percentage THD. Just be aware that it does depend on the load on the circuits of the, you know, the percentage content. So percentages can be a little bit misleading. But if we wanted to look at this this plot to actually work out, you know, what's a reasonable percentage current THD to apply for this installation, if you look at the normal working days, what you'll see on there is somewhere between maybe 10% to 15%, probably captures the regions. You know, we have got parts that go out towards 20%. So if we were going, you know, if we're trying to capture everything, we could be up towards 20% maybe, if we're actually, you know, trying to cover the full range. But if we went for 15 as a sort of typical value, again, we're in that sort of bracket. So that's still quite a big percentage of, you know, the current that is present in the harmonics. So that has an impact really with things like cable sizing and other things within the installation, as we'll see now. So in BS7671 Appendix 4, an equation is given for the calculation of the line current, including harmonic content. So you'll be familiar with IB, the design current, but we've actually got this one called IBH. So that's your design current, but corrected for the harmonic content. So it goes on to say in here, where other harmonics are present, e.g. 5th, 7th, etc., the heating effect of these harmonics in the line conductors has to be taken into account. For smaller sizes, less than 50 millimeters squared, so we're talking about 50 millimeters squared cables or less, less than 50 millimeters squared cables, the effect of harmonic currents can be taken into account by applying the following factor. So we can work out this factor C, correction factor H, for harmonics. And we can actually look at the harmonic content, and we can look at the size of the fundamental, and we can use this equation to actually work out this correction factor. Now, we'll talk about these in a little bit more detail in a moment, but actually in Appendix 4, they actually give us these cases. So they've actually got some worked examples, which are really useful to get an idea of what's going on. And in there, they actually give an example of working out IBH. So what they've done with IBH is they've said the fundamental current of the above load, and they give some detail in the case study there, is 58 amps. And it says, since the third harmonic content is between, so in the example, they use 20% THD. So it's between 15 and 33. The cable sizing is based upon the line current. And we'll look at that in a table in a moment. It's slightly out of sync here. Because the load has 20% third harmonic, the design current used for the selection of the protected device is given by. So what they do is they take the current, so the design current, they then multiply that by the square root of 1, so the fundamental they're saying is 1, plus 0.2 for 20%. They're both squared, added together. Square root of that gives a value for IBH of 59.1 amps. So you can see with the 20% third harmonic content, the design current has actually gone from 58 up to 59.1. Now you'll notice there is a bit of strange use of language here. They tend to get very confused, or the language is very confusing between third harmonic content and THD. So they seem to use the phrases interchangeably, and obviously if we were looking at just third harmonic content, that would be a different value to THD. But if we actually have a look at the next slide on here, there is a little note underneath. So in Appendix 4, rating factors are given based on third harmonic content. But the note below says that's expressed in percentage current THD. So the third harmonic content is expressed as total harmonic distortion. So rather than just looking at how much is in the third harmonic, or even how much is present in tripling harmonics, so the multiples of 3, what we're actually doing is we're taking percentage THD, which is the total harmonic distortion, not just that from the third harmonic. So there's a few things going on. So in the previous slide, we're correcting the line current based on the total harmonic content. And then what we're doing is we're actually applying a correction factor based on that content again, but for the tripling harmonics. And this is really to have the knock-on effect of the sort of the size of the neutral conductor, and making sure that the additive effect of the tripling harmonics is accounted for. So when I read this originally, it did look a little bit like double counting. It looked like they're sort of applying a factor to it and then they're applying a factor again. But I think what we're doing is we're actually correcting the design current based on the overall harmonic content using THD. And then we're looking at the effects of tripling harmonics, but they're also using THD as the sort of dividing line for the tripling harmonics as well. So there's a couple of things going on, and like I say, it feels originally like double counting, but I think it's just correcting the design current based on the harmonic currents, and then applying these rating factors on here. And how we decide on the rating factors is based on THD, because to be honest, most people, if you're carrying out a simple measurement, you could do a THD measurement, whereas if you wanted to measure what's just in, a certain harmonic, you would need more sort of advanced equipment for doing that. You'd need a PEL, or you'd need a power quality analyzer really to get right into that. So what's going on here is actually we're applying rating factors based on the percentage THD. So you can see that 0 to 15%, there's no real factor in there. It's just a factor of 1. So it doesn't really make any difference to that. If it's greater than 15 up to 33%, we're applying a factor to the line current of 0.86. And then once we go over that, we start applying these factors to the neutral currents. So again, this is where it starts to get, sort of more, say more involved really from that side of things. So it's great that we've actually got some examples that they've given us. In BS7671, it gives us examples of cable calculations with no harmonics. That's what they call case 1. 20% current THD, case 2. And 42% current harmonics. That's what they call case 3. And if you actually look at the impact, it's quite a significant impact on the actual the tabulated current carrying capacity required for those cables. So if we start off in case 1 where there's no harmonics, they calculate that we need a cable that will carry at least 85.2 amps. Whereas if we add in 20% current harmonics, that rises from 85.2 up to 99.1. And then if we take that up again, we take that up to 42% THD, we're then up to 125.8 amps. So again, you can see there's quite a spread there depending on the effects. Now, when we look back at the example installation we said we were talking sort of between 15 maybe to 20. So you can see there can be quite a difference in there when we start looking at installations and the figures that actually we should be applying. Now, in both cases 2 and 3, this actually requires the cable size to be increased from a 16mm squared all the way up to a 25mm squared. Although I do think case 2 I think was quite borderline, it was right on the edge. But it does show that actually based on the harmonics that are present and what we measured in the installation, and if we were actually doing our cable calculations correctly, it may actually increase cable sizes based on the harmonic content. And I would guarantee in a lot of cases, nobody is doing that. Nobody is actually carrying out those calculations and doing that properly. So it is important. And also in case 3, because it's talking about the neutral currents, it actually requires overload protection. And this is detailed in case 3. It actually requires overload protection for the neutral conductor. So that would actually be an overload protected device that monitored the neutral current as well. It didn't just work on the line currents. So again, that's increased overload protection as well. So not just have we got to make the cable size bigger, we've actually got to change the protection device as well. So you can see there, just out of those case studies, and I would advise anybody who's got a copy of the regs to go and have a look at those in more detail and just get your head around those, because they are very, very useful. And anybody doing any training courses or whatever, they're quite a good one there to point out as an example, that they've got them in there. Just be a bit careful. I say they do muddle their terms a little bit, and they equate THD with third harmonics and tripling harmonics and things like that. So they do tend to sort of mush it all together, but I think the general impact of it sort of makes sense in the end. You just have to read through it, but it's not the best writing in the world, I'll admit that. In this final section, we're going to look at Appendix 17, Energy Efficiency. A new informative appendix, Appendix 17, has been added to BS7671 to outline considerations for the design and erection of electrical installations to optimise the efficient use of electricity. The contents of this appendix are not requirements of the regulations yet, but are considered good practice and may be incorporated into the main body of the regulations, Part 8, in future editions. So that's an important point. I don't know if you're aware of that, but where you've got an appendix that says it's informative, or anything in the regulations that says it's informative, it's not actually part of the body of the regulations. It's not a requirement. You don't have to do it. It's there for information. It's informative. So at the moment, Appendix 17 and the contents of it are just there for information. They're not actually requirements to comply with the British standard, comply with the regulations. However, there is a statement, they actually put a line in there saying that it is intended that this appendix will be developed into Part 8 of BS 7671 in a future amendment. So they are telling us that this is going to get moved into the main body of the regulations, and at that point it's assumed that it will become normative. It will become actually part of the regulations. It won't be informative anymore. So in Appendix 17, there are many references are made to load profiling, similar to that shown earlier in the presentation. So earlier in the presentation, we showed you where we'd done a current logging exercise, and we looked at that over a period of a week. And generally, that's quite widely promoted and referred to in Appendix 17 of doing that type of survey. So in 17.4 here, design requirements and recommendations, it talks about determination of the load profile. And it says the main load demands within the installation have to be determined. The loads, together with their durations of operation and or an estimate of the annual load consumption of the main load demands in kilowatt hours, should be identified. So again, this is suggesting that we actually, we know what loads we've got in there and we determine what those loads are, and then potentially that we project them over an annual period of, what would the cost be over that period, or what would the demand be. Now, quite often we and in the previous example, we looked at current demand, so we actually looked at the amps. However, they are mentioning kilowatt hours. That's generally what we would call energy. So kilowatts, is normally power, and then you multiply that by time, and that's energy. So you have your energy meter within the electrical installation to measure your energy usage. So again, that's perfectly doable. That's just a different screen effectively when you're doing your surveys. So we can plot energy over time and actually look at what's going on within the installation and plot that just like we did with a current survey. It just depends what you're trying to achieve at the time, but that's it's a similar process. Now, moving on down there, it talks about data logging, and it says historical data, where available, can be input into can be input for making energy demand forecasts. To achieve a design capable of delivering high levels of energy efficiency, all available energy consumption data should be taken into account. So again, they're promoting energy logging or data logging as a useful activity to actually be able to get the best out of the highest level of energy efficiency that we can. And again, this is mentioned in the next slide, where it actually talks about, monitoring of the electrical installation. And in this top section, it says the installation should be designed to enable the measurement of its total consumption in kilowatt hours for every hour of each day. This data and the related cost of energy information should be logged and stored for a minimum of 1 year and be accessible to the user. So again, this is actually carrying out an energy survey and making that data available for the user. And at the bottom here, it actually talks again about setting up the electrical installation with an efficiency management system that monitors the whole electrical installation and enables us to optimize and actually get the best performance out of energy efficiency measures by actually monitoring that data. So this is quite important that it's actually saying we really should be going down this route. Now, it is important to note in Appendix 17, it does say that typically a lot of what's in here, a lot of the measures in here don't apply to normal domestic premises. So we are talking more about big businesses. We're talking about factories, maybe supermarkets, large energy users. So we at Chauvin Arnoux actually have customers who buy power and energy loggers to do initial surveys, but then they leave them installed after a period of time and they can dial into them remotely using the software and actually keep an eye on what's going on. So it is possible and very, very simple actually to get a power and energy logger, install that in an installation and actually give you the ability to do these things that it's referring to in Appendix 17. Now, a bit of a wacky idea, this one, but it is technically correct. So the idea of oversizing cables is also mentioned in Appendix 17 to reduce volts drop and thermal losses. So they're actually talking about making your cables bigger to reduce the losses within those cables. However, I have done some maths on this and I've done some examples, and in most cases though, the payback period on this type of measure would be many years, making for a poor return on investment. So often the price of that additional copper, to actually make the cables bigger, when you look at very small, it is very small savings. They are real savings, but it is very small savings. You would need that copper to be there for a long period of time. You would need a long life of the electrical installation before you would start actually making returns on investment. And when we look at energy efficiency, you start with what's going to make the biggest impact first. So again, really, there's a lot of examples of things you can do to actually save a lot of energy before you start getting down to making cables a little bit bigger to reduce your volts drop and reduce your sort of thermal losses in the cables. It is a fact. It is it follows the laws of physics, but when you actually look at the payback period and the return on investment, I think there's probably better areas to start your energy efficiency journey on than that. So more practical measures referred to in Appendix 17 include power factor correction and the use of high efficiency motors and motor control drives. Although remember, if we are adding in motor control drives, they can introduce harmonics. So you do need to be careful that there's a knock-on effect there, that when we're introducing, something because it's more energy efficient, there will be a trade-off there because there's harmonics in there and we have to allow for that. Power factor correction obviously is a very popular process, particularly in areas where we're using big inductive loads. However, it is important to make sure that they are designed, and set up for the installation and for the loads that you are using. We've recently seen examples where we've been out to site and actually seen, 20, 30-year-old power factor correction equipment still in operation, that was designed to correct the power factor for motors that have long since disappeared. And there's now drives there, there's new motors, but the power factor correction is still there. And in that case, obviously, that's having a detrimental effect. So we do need to make sure that if we are putting these measures in, that they are current, they are up to date. And this is part of doing these power quality surveys, these energy surveys, because you can make sure that the control measures that are there, or the energy efficiency measures that are there, are still relevant for the installation in the situation that as it sits. Because often there's a lot of additions, alterations, things like that go on, and nobody actually readdresses and goes back again to reevaluate these measures and make sure that they're still effective. So it is important when we're putting these things in to make sure that they are really, kept under review. And to be honest, it's something that I would expect as part of EICRs, to actually look at these energy efficiency measures that were put in, and things like harmonic content and stuff like that as part of EICRs. Really, it doesn't tend to be an area that's looked at very much now, but I hope in the future it'll be something that gets more widely adopted. So that brings us to the end of the main content of the webinar. So let's just go back and do a bit of a summary. So in this webinar, we looked at BS7671 18th edition and the requirements that relate to power quality and energy efficiency. We looked at the general requirements, particularly for parts 1 and part 3. We looked at maximum demand and loading and how to do loading surveys. We also looked at harmonics in a bit more detail and how to correct cable sizes for harmonics. And we finished up by looking at Appendix 17, the new appendix there that covers energy efficiency. And as I mentioned, it's likely that in future that will be coming into the main body of the regulations as Part 8. So obviously that was just a quick overview, and I would recommend anybody to get a copy of the wiring regulations and really have a dig in there and look at these requirements in more detail, because obviously during these short sessions we don't have time to really have a deep dive into these. But hopefully it's something that in future, you'll be aware it does apply to the installations that you're working on. And actually it's not that difficult. We just need to have a bit more thought and maybe, a bit more test equipment to actually look into these things and actually understand exactly what's going on with these installations and design them accordingly. So thank you for joining us on the webinar. If you like this content, we've actually got more webinars coming. So we're doing a webinar a month. So if you have a look at our website, cauk.tv/webinars, and on there we've got a list of all of our previous webinars that we carried out. And as I said, in about a week's time, we'll get this on the website as well. And we've also got our YouTube channel, and we're trying to promote our YouTube channel at the moment. So please go on there, please subscribe and get notifications, sign up for the notifications so that every time we put a new video up there, you'll get a notification, you can have a look. But I mean, I think this is about the 9th webinar that we've done. We've been doing these for a few months now. So we've got this range of webinars going. So there's loads of content on there already for, low resistance measurements, earth resistance measurements, power quality, all sorts of things that we've already got on here. So we've got a nice suite of webinars on there. They're all similar content to this. They're all similar duration. So again, real great content that we've put together there. So hopefully that's something you can go back and have a look at. Now, just to finish up, obviously, thank you very much for attending this session. It's always great to see such a good turnout on these webinars, and these webinars have been really, really popular. And obviously, that's why we do it, because we like to see the feedback that we're getting from the customers. So remember, before you go to the handout section and download the PDF copy of the presentation. And also keep an eye out in your email box for your certificate that'll be sent out after the event. Normally they go out a few days after we finish the event. We usually have 2 showings of the webinar. So we do 2 sessions, and then a bit after that, they'll be sent out automatically. If you haven't received it, just check your junk folder or something that it hasn't gone in there. But generally, they're sent out automatically, and that's pretty reliable system. We have got the webinars available on demand, as I said, on our website, www.cauk.tv, and we've also got them on our YouTube channel. And if you want more information, we've actually got a load of technical articles and other content available on our website, cauk.tv. So again, we'd urge you to have a look at that and go on there and sign up for the mailing list as well. And then when new content goes on, you'll be informed of that. So thank you very much for listening to the webinar today. If you've got any questions, you can type them into the questions box now, but hopefully we've answered those all through the session as we've gone. And I hope to see you again on another webinar soon. Thank you very much for your time.